Hello, in part one, we are going to be testing the solubility of different substances in water and trichloroethane. And I want to try to hold the phone here and take you through the different models and discuss the properties of these different things. Remember again, the motto for this lab, if you will, is like dissolves like. So polar substances like salts, ionic substances, which are salts, polar organic compounds are going to dissolve in water, which is a polar inorganic substance. And non-polar things, greasy things like hydrocarbons, are going to be soluble in greasy organic solvents that are mostly non-polar. So let's discuss some of these properties of the solvents first. Trichloroethane looks like this. I made a little molecular model of it. We've got 2 carbons in black, 3 hydrogens in white, and 3 chlorines in green. Now, chlorines are electronegative and slightly polar, but they're kind of all canceling each other out because they're going in different directions. There is a net polarity this direction towards my thumb where it's pointing, but it's very slight, okay? So this, by all accounts, is a non-polar solvent. It has a very large van der Waals surface that I can't show you with this ball and stick model, and it might interact with other organic things that are also non-polar, okay? Okay, so let's look at water as the solvent. Now remember, water is H2O. We've got the oxygen in red, and the 2 white marker balls here are hydrogen atoms, okay? And it has a bent structure. We're not showing the lone pairs on the oxygen atom. But remember that the oxygen is a more electronegative element, and hydrogen is less electronegative. So we put delta minus on the oxygen and delta plus on the hydrogen. I've always wanted to 3D print some of these with magnets embedded into the plastic so we could see how the delta plus of one of the plastic 3D printed things will stick or magnetically attract to another molecule with delta minus, but not the 2 white hydrogens, okay, because they're both delta plus, and I could simulate that with magnets if I had the time to do that. So each water molecule has a delta minus on the oxygen and delta pluses on the 2 hydrogen atoms. And if I grab a pencil here, I can indicate that the delta minus and delta plus are going to be attracted to one another, and we indicate that with a dashed line. A hydrogen bond is a dashed line, okay? So you know, this is infinite in 3 dimensions, but I'm just showing 3 molecules here of water, okay? So water is extremely polar because it has a net molecular dipole moment pointing in the direction of the oxygen. It has hydrogen bonding, okay? And so it's a very polar solvent, okay? Let's discuss now some of these substances we're going to be dissolving or trying to dissolve, okay? So the first one we're gonna do is sodium carbonate. Okay, sodium carbonate is an ionic compound. There are no bonds or balls or sticks between these two, these different plastic colored balls that represent the elements or the groups. So sodium ion is just a ball, you could think, and sodium ion is another green, okay? And carbonate, I'm just representing it by this, this one in the middle, okay? Now, the idea here is the Coulomb force, which is opposites attract, which is a Coulombic force or an attractive force between opposite charges. So, how are we going to indicate this? I don't know. There's no set way. We don't really draw this in chemistry, but I'll draw like a lightning bolt if I can kind of do that between these 2 different groups. Okay, so this sodium ion is attracted to the minus 2, and the minus 2 charge is attracted to the plus 1 charge here. Now in barium carbonate, barium is a much larger ion than sodium ion, okay? Because it's further down in the periodic table, it's larger. So I picked out this one here, which is a larger radius than that one, okay? It's also a plus 2 charge, as you can see. Now carbonate is still minus 2, so I'm still choosing the same molecular model kit piece for that, okay? Now a plus 2 charge and a minus 2 charge are held together more strongly because of the Coulomb force between these, okay? So, whoops, I meant to use a lightning bolt, didn't I? Now, the force between 2 different ions is equal to some constant, okay, times the charge of ion 1 times the charge of ion 2 divided by the distance squared. Now let's, really fudge this out and say that the distance between these two ions is about the same, okay? So let's do this one up here. If the force is equal to charge 1 times charge 2 over r squared, all right, the sodium ion is +1, this is -2, so the force is going to be equal to K times 1 times 2, over r squared, so it's going to be 2K over r squared, okay? Now down here, what is Q1? Q1 is the magnitude of the charge, which is 2, okay? And carbonate has a -2 charge. All right, and if the radius is the same, it's going to be 4 times K over r squared, okay? So you can see how there's a 4 in this bottom case and there's a 2 up here. So based on the charges, okay, we know that opposites attract, but the more charge you have, the more strongly attracted it is to each other, okay? So there's going to be more attraction between barium and carbonate than sodium and carbonate, okay? And that's why barium carbonate is insoluble. It's because of this Coulombic attraction. Now let's talk about one of the other substances we're going to be studying, okay? And that's naphthalene. So these pieces that form the vertices or the intersections are carbon atoms. Okay, so we're using gray here in this model, and the white balls again are traditionally hydrogen. Okay, so the molecular formula for naphthalene is C10H8, and this molecule is interesting because it's planar, but you can see how it's a hydrocarbon solvent. There's no electronegative elements here. This is not polar. All it has going for it is a van der Waals attractions. Naphthalene forms mothballs, and since these can stack together a little bit, they don't really form strong intermolecular forces, okay? And this substance can volatilize or sublime quite easily, and that's how mothballs just disappear, okay? So that's naphthalene, okay? So you want to think about what solvent that's going to be compatible with. Is it going to be compatible with trichloroethane, or is it going to be compatible with water, okay? So let's go ahead and do the chemical solubility test and see what it looks like.